My talk is about what the heck is system hyperpipelining, and I'm Tobias from Munich. I will have it a little bit shorter than this, but system hyperpipelining is based on C-slow retiming. So we'll talk about C-slow retiming, then system hyperpipelining, and some things you can do with it. So C-slow retiming, that's a simplification of a digital design. Let's say this is a bus, so you can simplify it like this. And when you add the same number of registers into each pass, you duplicate the functionality. So you make a copy of the design, and you use the logic in a time-sliced fashion. But you have to speak into the microphone? Sure. Because we talk about processors, let's talk about threads, and each color is a thread. So now you use the logic in a time-sliced fashion. If you unroll a three-stage pipelining, you can draw it like this. And when you apply C-slow retiming, you add registers all over the design, and then you have 3 times the functionality here. I skip through it because it's supposed to be a lightning talk, but the open risk 100 H_HP and the AVR_HP is actually a C-slow retimed core. You can download it, and you have a multi-threaded version of the core. The benefits are that compared to a standard implementation, this guy runs 3 to 4 times faster. So you increase the performance to up to 4 times, but on an FPGA it does not consume any more area because it only has a higher register utilization. The problem is that when you have timing critical path here, then now you have a lot of timing critical path all over the design. And this step is hardly to be done manually. So you need a tool for that, and I have a tool written for that. So it does this register insertion and timing-driven register insertion automatically on RTL level. So that's the point. In Berkeley, they did some research on doing on lookup table level, but whoever did some register balancing on lookup table level on an FPGA, it's impossible to do, especially when you talk about thousands of registers. So what is system hyperpipelining? Oh, maybe this is an interesting slide too, in terms of register placement. This is an observation I do since the last 20 years on almost all FPGA families. A lookup table net pair usually follows a Xi² function, and an unconstrained version. And when you fold this distribution, you get a Gaussian. So when you have multiple consecutive pairs, then you can easily estimate your timing. So I'm doing this since 20 years on a Altair Max the first time, and this observation is valid. So when you have more lookup tables, then this becomes 1, so it's not usable for large paths. But when we talk about C-slow retiming, it's very you only have 2, 3, 4 lookup tables between registers, and the rest is done by synthesis optimizations. Need to be a little bit faster here. So what is system hyperpipelining now? That's a key question. You replace the original registers now with memories, and you add a thread controller. And now you can run more threads compared to the C-slow retimed version. And you can stall a thread on a cycle-by-cycle base. And so C-slow retiming plus context switching is system hyperpipelining. You can remove registers into the memories and so on. I unfortunately don't have time to go into details here. So the point is that you have an original design with C-slow retiming, you have a fixed order of threads, and with system hyperpipelining, you have more threads, but the key is that you can dynamically switch between them, and you can have a performance balancing. So there are a lot of additional methodologies to improve based on that. So cycle scaling, depipelining, and out-of-order execution. So if you have, this is the original design, you now have system hyperpipelining, and you can have more threads. You have optimization methodologies to fill the pipelining. So the key point is also, I would like to mention that you can do this by hand, but it's a second level of pipelining. And to this extent, it's almost impossible to do this manually. And this is an automatic process to add this second level of pipelining. Because you increase the number of registers by order of you duplicate or triple the number of registers, and you have to implement them timing driven, and this is very critical. But working on that, I see a lot of enhancements on system level. So performance per area is one thing. The other thing is, for example, when you run virtual peripherals, like we had the minions, and when they use this, when they use a multi-threaded system hyperpipelined version, they can run way more virtual peripherals on it. So I have a paper on based on a Cortex M3 design in the current transactions. So I hope the minion guys will use system hyperpipelining on the minions to run virtual peripherals, very much efficient. And and there are other improvements on system level I'm working on. And just another idea is, or the point is that we have program memory, we have data memory, but what I'm actually doing is I'm having a thread state memory. So I'm saving the state of a CPU in a memory and use it on a cycle-by-cycle base. That's what I'm doing. And Jan, for example, when you would like to apply C-slow retiming on your monster, there's a potential to increase the performance. Yes, something like this.
My friend Burton Smith.
I'm already in the discussion, but that's it basically. So thank you. And Jan,
I think that there's definitely a role for these barrel processors, hyperpipeline processors, whatever you call them. My friend Burton Smith invented the Denel Core HEP and the Terra MTA. It was the way that we built memory latency tolerance for very area efficient cores, right? So if you want to go across to a memory system that's 10 cycles away and you don't want your processor to stop, it's lovely to have many thread contexts so you could switch to another one and do something useful with all of those gates in your data path. And then 10 cycles later, it comes back. The MTA was 128 thread contexts per processor, so you could go across the floor to the other cabinet where the memory was. And now, of course, modern GPUs also use this thread switch to absorb the memory latency tolerance there. So it's not only clock frequency, but it's also keeping the data path hot with useful work by having lots of thread context. Yeah.
So if anybody wants to work with this, I'm happy to talk to you, and yeah, thank you for
Hi.